students, good morning. Today we'll continue the coordination chemistry and it is lecture number 9. Okay, so in the last class you have studied calculation of crystal field stabilization energy in case of octahedral complexes with strong field. Okay, today we'll do the same with respect to weak field ligand. That means when the weak field approaches the metal ion. Okay, so the splitting of d orbitals takes place in the same way, but the difference is here delta O is a less than pairing energy. Okay, in case of strong field delta O, it is greater than pairing energy. Okay, so this is in case of strong field and this is in case of say weak field. Okay, so okay, this you have to remember. So that means this relation helps you to calculate the crystal field stabilization energy. Okay, so the explanation is same way. When the ligand field is quite away from the metal ion, all the 5d orbitals are at ground state, there is no interaction, and when they are quite nearer, when they surrounded the metal ion spherically, so then all the 5d orbitals are at equal distance from the ligand field, and hence there is an interaction, and the energy of all the 5d orbitals is raised by same amount of energy. Okay, thereby the energy of d orbital is raised. It is shown like this. This is excited state, but still they remain degenerate. Okay, so further splitting takes place the same way. Say 3 of them are lowered and 2 of them are raised. That means the 2 orbitals which are lying exactly on the path of approaching ligand. It means after this the ligand field is not spherically symmetrical. That means surrounded the metal ion, and that is now it is disturbed, or it itself is set into, or it is concentrated at a particular positions around the metal ion. So, okay, and the positions are in such a way that 2 of them are lying on exactly x-axis, other 2 along y-axis, and the next 2 they are on z-axis. So these 2 orbitals which are lying along the axis, hence they experience greater repulsion than those which are lying in between the approach of ligand. So the splitting is like this, and the energy delta O in case of weak field it is quite less, and it is less than the pairing energy. Okay, now with this background, say we'll go for calculation of crystal field stabilization energy. So the same formula minus 4dq, and here dx system, that means the number of electrons present in d orbital of valence shell of metal ion, and this is equal to p plus q. So p is the number of electrons occupying or present in the T2g orbital. Q is the number of electrons occupying the EG orbital. So electronic configuration. So in yesterday we have seen the electronic configuration is T2g. It is T2g raised to P and EG raised to Q. Is it? So now say the metal ion is containing only one electron. So the maximum capacity, the D may contain 1, 2, 3 or maximum of 10 electrons, because the capacity of d orbital is 10. Okay. So when there is only one electron, it occupies lower energy. That means it lowers the energy of the system or the metal complex by minus 4dq. Okay. So the second electron, the metal ion, if it is having 2 electrons in its valence shell, so okay, or second that it enters the lower energy according to Alpha principle. Okay, and the third electron, if the metal ion is having 3 electrons, then that third electron is also enters the lower energy. So now when there is a fourth electron, D4 system, the fourth electron goes to higher energy level. So 1, if it is having 4 electrons, 1 electron, second electron, third electron, and fourth goes to the higher energy level, because delta O is less, P is greater. So difficult to pair up here, and it is easy to go to the higher energy level, hence it goes to higher energy level. So the 3 electrons are at lower energy level, they decrease the energy of the system by minus 12, minus 3, minus 4 into 3, minus 12 dq, and the one which goes to the higher energy level, that increases the energy by plus 6 dq. So thereby, when there are 4 electrons, in case of weak field, the crystal field stabilization energy is minus 6 dq. Okay. So when there are 5 electrons, so the 3 electrons goes to the lower energy and 2 goes to the higher energy level. So thereby equal amount of energy, here it is decreased and here it is increased. Thereby it is 0. Minus 12 dq plus 12 dq equal to 0. So now the 6th electron, once again it goes to the lower energy level and pairing starts, and therefore minus 4 dq plus 1 pair. Okay. And say D7, similarly it goes to the lower energy level. 2 pairs are forming, minus 8 dq is the energy. And 8th electron, suppose metal ion is having 8 electrons, then the 8 electrons will be distributed like this, and energy calculation according to this, so it comes minus 12 dq plus 3p. So 9th electron, it will pair up at higher energy level. So now here it is minus T2G6 Eg raised to 3, and therefore minus 6 dq plus 4p. And 10 electrons, they are distributed like this, all the orbitals are completely filled, and the value of crystal field stabilization energy with the D10 system is like this. Okay. So in the examination they may ask you to calculate D5 system or calculate D4 system, either with weak field ligands or with strong field ligands, or sometimes they may ask both. So what is the crystal field stabilization energy in case of octahedral when the field strength is weak and when the field strength is strong? So you should be ready, and here main thing is you have to remember this relation. Okay. So with this we'll continue in the next class. Thank you.